Bismillahirrahmanirrahim. I am Dr. Syed Azhar. In this lecture of linear algebra, we will discuss subspaces. A subset W of a vector space V is called a subspace of vector space V if W is itself a vector space with respect to the same vector addition and scalar multiplication. Means a subset W will be a surface of a vector space V if it satisfies all the 8 properties of a vector space with these vector addition and scalar multiplication which is used in this vector space. So it is quite laborious to check all these properties for a subspace. Here we have a theorem which states that a subset W will be a subspace if number first that W set contain a zero vector and for every uv vector belong to subset W and scalar k u plus v and k times u both will belong to subset W. It means that this W set will be closed with respect to addition and scalar multiplication. Instead of these two conditions, you can also check AU plus BV belongs to W for every scalar A and B. These two conditions and this one, these are equivalent conditions. So for a subset, we will check only these two conditions instead of all those 8 conditions which we have discussed in previous lecture of linear algebra. In this example, U is a subset of R cube and this U subset contains those vectors whose components are equal. So we have to check whether this subset U is a subspace of R cube or not. So we have two ways. The first way is we have to check all those 8 conditions of a vector space to check this subset U. And the second way is to apply the theorem. And for a subspace, that theorem has only 2 conditions. The first one is zero vector and the second one is some constant say k1 u1 plus some constant say k2 into u2 and this combination will belong to this subset U. Look at this straight line. This straight line is basically representing the subset U. And this straight line is passing through the origin. So clearly the subset U has a zero vector. In this zero vector, look at the components. All the 3 components are zeros, means all the 3 components are equal. So that's why this zero vector is contained in this subset U. In the second condition, let us take 2 vectors U1 represented by A1 B1 C1 and U2 represented by A2 B2 C2. Clearly, according to this definition, A1 B1 C1 will be equal and A2 B2 C2 will also be equal. And for scalars K1 K2, let us take in the second condition, basically we have to check this result K1 times U1 plus K2 times U2. So that's why let us take K1 times U1 plus K2 times U2. K1 into U1 vector which is A1 B1 C1 plus K2 into U2 vector which is A2 B2 C2. Now multiply K1 with A1 B1 C1 and K2 with A2 B2 C2. We will get this expression. And then add these 2 vectors, we will get K1 A1 plus K2 A2. Similarly K1 B1 plus K2 B2. Similarly K1 C1 plus K2 C2. We added these 2 vectors component wise. First component with first, second with second and third with third. Now we know that A1 equals B1 equals C1. If we multiply scalar K1 with these three, we will get K1 A1 equals K1 B1 equals K1 C1. Similarly, we know that A2 is equal to B2 is equal to C2, and if we multiply K2 with these three, we will get K2 A2 is equal to K2 B2 is equal to K2 C2. Now, if we add them, if we add K1 A1 with K2 A2, we will get K1 A1 plus K2 B2. Similarly, if we add K1 B1 with K2 B2, we will get K1 B1 plus K2 B2, and the remaining terms K1 C1 with K2 C2, we will get K1 C1 plus K2 C2, and all these three conditions will be same. Now look at these components. This first component is our K1 A1 plus K2 A2. The second component is this one, K1 B1 plus K2 B2, and the third term is K1 C1 plus K2 C2. And since all these three are same, so this shows that all the three components of this vector are same. And when these components become same, then we say that this vector will belong to subset U, because this subset U contains those vectors whose components are same. So that's why this vector belongs to U. Since U satisfies both the conditions of the theorem, that is, zero vector belongs to U, and this scalar multiplication and addition of vectors also belongs to subset U. So U is a subspace of RQ. Here we have a result. The intersection of two subspaces is also a subspace. To show this result, let us consider we have two subspaces represented by U and W of vector space V, and we have to show their intersection. U intersection W is also a subspace of this vector space V. Since U and W are the subspaces, so both these subspaces will contain a zero vector. That is, since U and W are subspaces, so both have zero vector. Since zero belongs to both subspaces, so zero will belong to their intersection, and this is the first property of a subspace. For the second property, since we have to check U intersection W, so let us take two vectors V1 and V2 from their intersection U intersection W. Since we take these two vectors from the intersection, so by the property of intersection, these two vectors will also belong to U and W also. Since U and W are the subspaces, and we know that subspaces satisfy the closure property with respect to addition and scalar multiplication, so that's why K1 V1 plus K2 V2 will belong to subspace U, and K1 V1 plus K2 V2 will also belongs to subspace W, as U and W both are the subspaces. Since this combination belongs to U as well as W, so this combination will also belongs to their intersection. That is, K1 V1 plus K2 V2 belongs to U intersection W, and this one was the second condition of the theorem. And that theorem tells us if a subset satisfy this condition and this condition of a linear combination of vectors, then we say that that subset is a subspace of a vector space. So clearly here U intersection W is a subspace of a vector space V. Remember, we know that U intersection W is a subset of U as well as U intersection W is a subset of W. So this intersection of subspaces will also be a subspace of U as well as W. We have another example, and in this example let our vector space is consist of square matrices of order n cross n, and let W1 be the subset of all upper triangular matrices of this same order n cross n. First of all, you have to know about upper triangular matrix. Upper triangular means if the entries below the diagonal are zeros, then such matrices are called upper triangular matrices. And here we have to show that this W1 is also a subspace of M cross N matrices collection. Since zero matrix of order M cross N is also a special type of an upper triangular matrix, so clearly zero matrix belongs to W1. In the second condition, we know that the addition of any two upper triangular matrices gives us an upper triangular matrix. Similarly, any scalar multiplication with upper triangular matrix gives us upper triangular matrices. It means that upper triangular matrices are closed with respect to addition and scalar multiplication. So this shows that W1 is a subspace of vector space V, and V is a collection of square matrices of order n cross n. Now let's discuss something new. In the xyz plane, say this one is our x-axis, this one is our y-axis, and this one is our z-axis. In previous examples, we studied that a straight line passes through the origin, form a subspace for this xyz plane. Look at this straight line. This straight line will also form a subspace for the xy plane. But if we take this straight line, since this straight line is not passing to the origin, so this straight line will not make a subspace for this xyz plane. Now look at the xyz plane. Since this one is our x-axis, this one is our y-axis, so this whole region will be our xy plane. Similarly, since this one is our y-axis and this one is our z-axis, so this one will be yz plane, and similarly this one will be our xz plane. Now look at the planes. Look at this whole xy plane. Since this whole xy plane passes through the origin, so this xy plane contains the origin. And all these planes, xy plane, yz plane and xz plane, all these planes are basically square vector spaces. And we know that R square form a vector space, so this shows that all these planes are the subspaces of xyz plane, as these are the subsets xy, yz and xz. All these are the subsets of xyz plane, and so all these subsets passes through the origin and satisfies the addition and scalar multiplication properties. So these planes are subspaces for the xyz plane. This is the end of today's lecture. Feel free and ask questions in the comments section. Thank you.